There are many ideas that we take for granted as fact in the modern day, but some of these were not quite as easy to prove as they may seem now. So today, I would like to take you through the nearly 200-year-long journey to prove one of these supposedly basic facts. An idea that literally moved the Earth. Heliocentrism. For most of history, Earth was believed to be the centre of the universe, unmoving, while everything else revolved around it. This idea is known as geocentrism. It was so deeply ingrained into society that it was even a part of Christian belief. Earth is special, it's the home of humanity, so God must have placed it in the centre of the universe for us, was the predominant belief for a very long time, and any ideas counter to this were considered heresy. There was a problem with the geocentric model though. If the Earth was at the centre, the orbits of the other planets had to be very complicated and erratic to match our observations. If God had put so much care into our place in the universe, surely he would have put a bit more care into how the other planets orbited around us. This led some astronomers to try to come up with a new, more elegant model of the universe. In 1515, a Polish priest named Nicolaus Copernicus had a revolutionary idea. What if the Earth moved? So he proposed a new heretical model of the universe, heliocentrism, the idea that the Earth and all of the other planets actually orbited the Sun. However, he did not initially publish this theory, although some say it was because of scientific shortcomings with his theory, rather than fear of criticism from the Church. It wasn't until 1543, the same year of his death, that he finally published the theory. Despite the general idea being correct, very few people took it seriously, and those who did potentially faced serious punishment from the Church. One man named Giordano Bruno was even burnt at the stake for teaching heliocentrism and other heretical ideas. One astronomer named Tycho Brahe later proposed what was essentially the same model as Copernicus, but still kept the Earth at the centre, with the Sun orbiting the Earth and every other planet orbiting the Sun. This may seem silly now. If you're going to say all the other planets orbit the Sun, you may as well go all the way and say the Earth does as well, right? But this just goes to show just how deeply ingrained geocentrism was at the time. However, as stated earlier, it was not just religious beliefs that led people to dismiss Copernicus' theory. There are also a few holes in it. Copernicus believes that each planet orbited in a circular motion with the Sun at the centre. There were two main issues with this. The first was that it did not produce more accurate results of the observed movements of the planets. Why risk switching to this radical new model when it didn't even provide astronomers any benefit? The second was simply that Copernicus had no proof, no observations to back up his claims. So unfortunately, Copernicus passed away before he could see the mark that he would make on history. But the idea that he planted with his theory would eventually change the world as we knew it. In 1600, German astronomer Johannes Kepler became the assistant to Tycho Brahe. Brahe had amassed an incredible collection of astronomical records, which his model of the universe was based on. He distrusted Kepler, though, and kept most of these records from him. But there was one thing he could not get his head around: the orbit of Mars. So he tasked Kepler with trying to define Mars's orbit, hoping that he would also be unable to achieve this, and therefore unable to spend any time on any research that Brahe would not approve of. Ironically, though, this gave Kepler exactly the opportunity he needed to do what Brahe had feared most: perfect the heliocentric model. The issue with Mars's orbit is that it wouldn't fit into a perfect circle no matter what Brahe tried. Based on his observations, there appeared to be points when Mars was closer to the Sun and points where it was further away. However, Kepler also noticed that a line between Mars and the Sun would sweep out an equal area at equal times, no matter what part of the orbit Mars was in, a fact which would later go on to become Kepler's second law. If the orbit were a perfect circle, this would be true. But otherwise, how could this be the case? Imagine we have two spheres, A and B, a distance r apart, with sphere B orbiting sphere A in a perfect circle. Let's say it takes 5 seconds for B to complete one rotation around A, called the period. If we imagine a line connecting the two spheres and trace out the area of this line for 1 second, we get this sector. We trace the area for 1 second, a fifth of the total period, so the area of the sector will be a fifth of the total circle, pi r squared over 5. This will be true no matter where B is when we start tracing. However, if we now let B orbit in an ellipse around A, with closest distance, called the semi-minor axis r1, and furthest distance, called the semi-major axis r2, these areas will change and no longer be equal. Let's go back to Mars now. The orbits of the planets, including Mars, are only just barely elliptical, meaning that the sectors around each axis will be roughly the same as a sector of a circle with radius equal to that axis. When Mars is at its semi-minor axis, that will be about pi r1 squared over 5. And when it is at its semi-major axis, it will be pi r2 squared over 5. As r2 is slightly greater than r1, the area of its sector will be slightly greater, contradicting Kepler's second law. To resolve this, Kepler assumes that Mars must move faster when it's closer to the Sun and slower when it's further away. This led him to the discovery of what would become his first law, that the planets orbit in ellipses, with the Sun not in the centre, but at one of the two foci, a point between the centre and the edge along the semi-major axis of the ellipse. And so, in 1609, Kepler published these alongside his third law, that the square of the period of a planet's orbit is directly proportional to the cube of the semi-major axis. Basically, that a planet takes longer to orbit the Sun if it's further away, as Kepler's laws of planetary motion, finally giving us a perfect heliocentric model. Just 1 year later, Italian astronomer Galileo Galilei made two very important observations. Observations that would see him face charges of heresy and be placed under house arrest for the rest of his life. First, he observed that moons orbited Jupiter, proving that not everything in the universe orbited the Earth. And second, he observed the phases of Venus. Just like how the moon has phases, so do the planets, and the cycle of Venus's phases proved that it must orbit the Sun. So now we had a perfect heliocentric model, which produced far more accurate predictions than the old geocentric one, and observations to back it up. So that's it, right? Well, not quite. It turns out there was one more issue, which had yet to be addressed by anyone. Why? Sir Isaac Newton needs no introduction. The English mathematician and physicist revolutionized physics with his discovery of gravity and the laws of motion in 1687. Every object remains at rest unless acted on by a force. An object's force equals its mass times acceleration, and every action has an equal and opposite reaction. This discovery had a tremendous impact on science as a whole and unified and solved many different problems with the same solution. And that word, unified, is exactly what was missing from heliocentrism until now. Why do the planets orbit the Sun? Why do they speed up when they get closer to it? If the Earth really is moving, why do we not feel it? Well, as it turned out, these questions, along with many others, could all be unified and resolved by the same laws of motion. One thing I've neglected to mention throughout this video is why people even believed in geocentrism in the first place. One main reason is actually pretty logical. If you throw something in the air, it falls back down to Earth, right? Well, people naturally assumed that this meant the Earth must be in the bottom of the universe, which evolved into placing it in the centre when people realised that the Earth was not flat. Another, arguably more important reason is one that I briefly touched on at the beginning of this video. Elegance. Elegance was the main driving force behind many proposed models of the universe at the time, as the old geocentric one was just too messy. However, it is also what led to many of the mistaken beliefs that hindered heliocentrism for so long. The idea that the planets had to move in perfect circles, at constant speeds and with the Sun directly at the centre, which we now know are all wrong, all stemmed from trying to make the model more neat and more elegant. Copernicus' idea, Kepler's model, Galileo's observations, Newton's laws, they didn't fit this. They were messy, whether visually or ideologically, but mathematically, I would argue that they were the most elegant of all. So, why do the planets orbit the Sun? Because the Sun has a much greater mass and therefore a greater gravitational force. Why do the planets speed up when they get closer to it? Because the gravitational force, and therefore the acceleration, grows stronger at closer distances. Why do we not feel the movements of the Earth, and why do objects fall back down to it? Because of the gravitational force between us and the Earth. All of these questions, every missing piece, every aspect of heliocentrism finally explained with one unifying force: gravity. And what could be more elegant than that? Thank you so much for watching. This video was made as coursework for my degree, so if you have anything to say, please let me know in the comments and fill in the Google form in the description. And if you enjoyed, go check out Orb on the Movements of the Earth, an absolutely incredible anime all about heliocentrism, which this song and the idea for this video came from. Thank you.